Folks, let's look at the work energy theorem. The work energy theorem, guys, before we define it and says what is it, it's very important to understand certain things about it. Now, if you read here on what I've written here, it says when a net force, I want the highlighter, when a net force works on an object, the object moves faster or slower. Guys, all the time when the net force is not equal to zero, net force is not equal to zero, which is it's Newton's second law. It's Newton's second law. That means the object it's either moving faster or slower, is accelerating or decelerating. Now, if the object is moving faster, guys, let's say it's moving faster. What does it mean? That means that object, its initial velocity is smaller than the final velocity. That means that there's a change in kinetic energy, right? If the object is slower, that means its initial velocity is bigger than the final velocity. It's slowing down over a distance, or a displacement. Then the object experiences a change in kinetic energy. Guys, if the object is moving slower or faster, there is a change in kinetic energy, right? So that's what is important. And when an object, there's a net force, the net force is not equal to zero. That means the object is not the object's acceleration is not equal to zero. So when an object is moving faster, its acceleration is bigger than zero. When an object is moving slower, its acceleration is less than zero, right? Okay, guys, when an object moves faster, the net force is in the same direction with the displacement. Let's say this object is here and is moving faster. The initial velocity will be smaller than the final velocity if it's moved faster. The F net will be in the same direction if it's moving faster. But now and even the acceleration of an object, the acceleration, it will be in that direction. The direction of the acceleration will be in that direction. But now let's look at a case where the object is slowing down. The F net will be in this direction while the object is slowing down in this. And if it slows down, that means the initial velocity will be bigger than the final velocity. Even the acceleration direction will be in that direction while the object is displaced that way. Now let's go to the work energy theorem. What is the work energy theorem? Now, from what we said, now the net work done on an object is equal to the change in kinetic energy of an object. So if an object, the work energy theorem works on an object, it's speeding up or slowing down when it's Newton's second law. So the work energy theorem, guys, it says that the net work done, which is the sum of the work that has been done by the forces acting here, it's equal to the change in kinetic energy, right? The net work done on an object is equal to the change in kinetic energy of an object. So the net work done, which is the work that has been done by the forces acting on the object, is equal to the change in kinetic energy. And then we know the change in kinetic energy, it's kinetic energy final minus kinetic energy initial. Again, on an object that is moving faster, it's a Newton's second law situation. Let's say here's an object is moving faster and it's moving in this direction, so it's displaced from there to there. Now, when an object is moving faster, guys, again, its initial velocity is bigger than its initial velocity is smaller than the final velocity. Its velocity increases. That's what it means. And in that case, the F net, the acceleration will be greater than zero, and your F net will be greater than zero, which will be positive. Your acceleration will be positive. So an object that is moving faster, your F net is in the same direction with the displacement. Once the F net is in the same direction with the displacement, that means the angle between them is what? Is zero. That's what is written here. F net in the direction of the displacement is zero, and the work net is going to be positive. So when you calculate the work net here, is going to be positive using that formula that says work net is equal to F net change in t cos theta. It will be positive, right? This is what I said here. The final velocity is greater than the initial velocity, right? Now when an object moves slower, let's say this object is moving in this direction, but it moves slower. Now, when an object moves slower, that means the initial velocity is bigger than the final velocity. That means the acceleration is less than zero, the F net is less than zero. That means if it's less than zero, the F net, it will be in the opposite direction. So your F net, while the object is moving this way, the F net is going in this way. And then the displacement. So if you're looking at the F net and the displacement are going in opposite direction, they're parallel to each other. So the angle between them is 180. So if you calculate the work net of an object that is slowing down, so it will be F net change in x cos theta. So in the place of theta here, you substitute 180. While here, the angle is 0, you substitute what? 0 degrees. So here you substitute, so you get a negative net work done in an object that is slowing down. It's very important, guys. Let's look at an object when it moves at constant velocity. Constant velocity, it's a velocity that is not changing, guys, and the acceleration of a constant velocity is equal to 0, and the F net is equal to 0. That's what is important. Constant velocity, it's Newton's first law. It's law of inertia. Guys, if something moves at constant velocity, that means the initial velocity is equal to the final velocity. It's constant. It does not change its velocity. Therefore, what it means, the change in kinetic energy will be equal to 0, because the kinetic energy, okay, let's start. The change in velocity, it will be 0 because it's velocity final minus velocity initial, because this velocity is the same. So if it's 2, it's going to be 2 minus 2, it will be 0. So change in velocity is 0 and the kinetic energy is 0, right? When an object moves at constant velocity. Now, if the change in kinetic energy is 0, from the work energy theorem that says work net is equal to the change in kinetic energy, that means if the kinetic energy is 0 on a constant moving velocity object is equal to 0, that means the work net is equal to 0. And that's what it means, guys. It's very important. When object moves at constant velocity, the kinetic energy is 0. The change in kinetic energy is 0. The work net will be 0. That's what it means, guys. It's very important. Now let's look at in this diagram. This object is displaced this way, and it has two forces, and these forces are balanced, guys. It's very important. It's balanced forces. When an object moves at constant velocity, these forces are balanced, but in my diagram they don't look balanced, but they're balanced. Now, in order to calculate whatever that we're calculating, you say when work net is equal to change in EK, here this is what you do. You say the kinetic energy is 0, right? Because it moves at constant velocity. And then the work net is going to be the sum of these forces that are doing work. Remember, there's a normal force and the gravitational force there, but they're not doing work there. So it's going to be the work done of first force 1 plus the work done of force 2, right? And then the work done of force 1, you say force 1 change in x cos theta plus force 1 change in x cos theta equal to 0. Okay, let me write that theta correctly. Cos theta, right? Now, when we substitute there, you have force 1, whatever force 1 is, and the displacement, whatever it is. But when it comes to force 1, if you look at force 1, its displacement is in opposite direction with force 1 is in opposite direction with the displacement. So it's going to be cos 180 plus whatever it is, force 2. This is supposed to be force 2, and then the displacement is the same, cos. And when it comes to force 2, look at force 2. Force 2 is in the same direction with the displacement, so it's going to be 0 degrees, the angle equal to 0, and then you get the unknown, whatever that was an unknown there. I hope that makes sense.